so to normalize everything to 1, just to establish a good language for describing the polarization state of light. So when we do it, then the X polarization light is expressed like this. That is quite simple. If you care about the power calculation, then you just put some amplitude in front of it. Okay. But now we understand that if we have 1, 0, this means that if we define x-axis to be in the vertical direction, then we have the vertical polarization or X-polarized light described by this. And likewise, we can define the polarization Y-polarized light with this very simple vector, because you have 1 along the Y direction, okay? And sometimes we call this as a vertical polarization, this is a horizontal polarization with the subscript like H and V. And we can also define the 45-degree linear polarized light. If we have this normalization, then we need to have this 1 root of 2, 1 over root of 2 in front of it. Okay. If you try to do this calculation, then you'll be ending have 1/2 plus 1/2 equal to 1. So that's why you have a normalization factor in front of this. Okay, is there any question about this? So far, it's quite straightforward. Okay. Everything is normalized to 1 when you talk about Jones factor. But if we need to keep track of the power or intensity, then put an amplitude in front of it. Okay. Now, when we comes to the point about circular polarization or elliptical polarization, then we have minus GA plus GA right here. But we talk about I before, right? And you can go through the process to see that if I have minus GA, it's right-hand polarization. When I use GA, I told you that this is an engineering notation. And for engineering notation, people like to talk about right-hand polarization or left-handed polarization. When we talk about optics notation, people like to talk about right polarization and left polarization. So this is a right polarization, this is a left polarization. Okay, right-handed polarization is left polarization, going like this. And left-handed polarization is the right polarization, they're taking like this. And the corresponding G notation is like this. And this is the table. You can just keep it as a reference. Okay. So if you sort of make it consistent on this page, then you'll be able to read engineering textbook. Okay. So this is sort of additional I want to give you so that you get used to the different notations in engineering textbook and optics textbook. All right. So this is Jones vector. Well, the good thing about Jones vector is that if you use it as the input, then you will get some output after propagating the light through some elements. Okay. So let's check the property of the Jones vector. Well, if I have a Jones vector, 2 Jones vectors for 2 polarization of light, you can check whether or not the polarizations are orthogonal or perpendicular to each other or not. Just do this intensity calculation. If you get no intensity when you do this vector calculation, this is transpose of E1, and this is conjugate, converse conjugate of E2. If you get nothing, this means that the two polarization states are orthogonal to each other. And you can quickly do a check. For example, if you have this linear polarized light denoted by 0, 1 for the Jones vector, and for this polarization state of light denoted by 1, 0, then you finish this calculation to get nothing. Okay. So this is how you check whether or not the polarization state of light are orthogonal to each other. And another thing is that this is a 45-degree polarized light, and if you have this is a 45-degree polarized light. If I have a 90-degree rotation, then do a check on this from this calculation, you get nothing. So this means that these two polarization are perpendicular to each other. But the perpendicular polarization is just one concept of orthogonality. The orthogonality concept, in fact, includes the circularly polarized light or elliptical polarized light. So if you do this calculation for left polarization and right polarization, or right-handed polarization, left-handed polarization, then you end up having nothing. Okay, so this means that these two polarization states are orthogonal to each other, although the electric field vector is not perpendicular to each other. Okay, but the concept of orthogonality applies to the sense of rotation of the polarization state. Okay, so this is how you check whether or not the two polarization states are orthogonal to each other, and then you can sort of use this to create some darkness in on the screen, for example. Okay, for example, if we put two polarizers with transmission axis to be perpendicular to each other, then you can create complete darkness. All right, so let's try to understand the usefulness of Jones vector and Jones matrix. Once you have the Jones vector, you can have the input and output, but if you propagate some light through some element, then we can try to create some matrix, some operator on the input so that I can deduce the output of the polarization. And this is very similar to ABCD matrix, the concept of the ABCD matrix. If we can do this calculation, then we can put everything into a computer and then finally figure out the polarization state of light. Okay, so this is the reason that the Jones vector, Jones matrix are so useful. All right, so to think about the ABCD matrix for the linear polarizer, what for the X polarizer, you allow the transmission of the X polarized light. So you put the transmission axis of this along this direction. And the corresponding ABCD matrix is given by this. Now we call this Jones matrix. Okay? But if you put the transmission axis of this polarizer along the vertical direction, then you have this Jones matrix. So this is the simplest form, and you can easily, like, for example, 1001, if you have any Ex input, E1 input, you end up preserving this term. And this is your output. This is your output, the Jones vector. Okay, you're preserving this term. So this is indeed the X polarizer, the Jones matrix of the S polarizer. Okay. All right. So wave retarder is expressed by this matrix. You introduce one phase difference to the one component of the electric field. Okay, so this is a wave retarder, and you knew that if this phase difference is plus minus 180 degrees, it's halfway plate. So if you have a linear polarized light go into this wave retarder, you can do polarization rotation. Okay, and if you have the circularly polarized light as the input to this wave retarder, having this 180 degree phase difference, then you can change the sense of rotation of the light. So this is what we just discussed a while ago. And then you can have a polarization rotator. Polarization rotator is that is this guy. Polarization rotator. Polarization rotator is this guy. Okay, if you rotate this with the angle theta, then you can obtain the polarization rotator expressed by this expression. And we're going to derive it. Okay, we're going to derive it. And so the convenience is that you can send your input of light, through a series of polarization manipulators, one by one, and finally get the output by multiplying those matrices together. So you see that the sequence is omega 1, 2, 3, 4, 5, and then the order, but in fact, no, I make it wrong. So the first element here is going to be 1, and this 10, and minus 1, and then this will be the last one. Okay, so you need to be correct on the sequence of this formula. Very similar, well, this is just the same as how you write down the calculation for ABCD matrix. Okay, the first element is going to go next to your, by the way, this is input. So this is your input. So somehow I mess up this expression a little bit. And then eventually you have output. All right. So this is the thing I want to tell you. You have an input, Jones vector, and then you go through a series of the components that manipulates your polarization state, and finally you have an output. So you get the output Jones vector. Okay. So this is how you use Jones vector and also Jones matrix to get an output, the final answer. Okay. So it's quite convenient, as you have to learn it when you learn the ABCD matrix. All right. So now we learn about how we rotate this element with the angle. So sometimes we need to flip ourselves with the angle. Okay. Well, this is the polarizer. For example, the transmission axis is along this direction. What if I rotate this with the angle? Then it's easiest is that I also rotate myself with the angle, so that this does not quite change, right? So if I have a polarizer like this with the transmission axis along the along say x direction. Now I rotate with the angle. Then it's better that I also rotate myself with the angle. Then this does not change. But then when I try to analyze everything back to normal, this is horizontal, this is vertical direction, I need to be able to describe the results. Okay, so I need to be able to do polarization to do the coordinate rotation back and forth to make a conclusion. Well, the important thing is that, well, this is, right now, it's very easy to understand. It's like this. Well, if I rotate it with an angle, it's better that I also rotate myself with an angle, right? But then I always need to go back to the normal life. I need to be able to, finally I get a result, but I need to flip back. So that is why we talk about coordinate rotation. And I know that you'll be fainted as I talk about this. But let's go through this a little bit. Right, so you have a vector in space. This is the electric field vector in space, defined in the laboratory frame. What if I rotate this coordinate by an angle, but still I have a vector? How this vector is described by this prime coordinate system. So this is how we calculate that. And I think most of the Taiwanese students already learned this in high school. Am I right? All right. So the good thing about going to a foreign country is that we have different experience, and so sometimes we get shocked. Sometimes the common sense is not a common sense anymore. So anyway, but this is just some sort of figuring out sine, cosine, and so on to express the same vector in the prime coordinate system. All right, these two are the same vectors, but this one is described in this upright coordinate system, and this is the vector based on this tilted coordinate system. And then figure out the sine and cosine, figure out the relationship, and then you finally get a rotation matrix to relate these two coordinates in the prime and unprime coordinate system. Okay, so this is the rotation matrix you want to use for your calculation. But be patient. Just go through this sine and cosine. You'll establish here, and then get this relationship. And the same thing, if you rotate the coordinate system with the minus theta, then you come up with minus theta rotation matrix. Okay, and you're going to see that these two forms the inverse matrix. These two forms the inverse matrix. If you multiply these two together, you end up having a unitary matrix. It just means that you rotate the coordinate and then rotate it back. That's it. Okay, so nothing will change. I'll give you this. All right, I want to keep my promise. If you want to have right lunch with me in the university coffee, you can catch me. I need to go to the bank opposite to the coffee to pay you. All right, so you can head over. Who can handle this for me? You need to deal with the equipment, right? Yes. So perhaps you can. You want to go? Yeah. Okay. You just handle the all the order for the student who are interested in going, and then